Hello, hello. Okay, let's start, everyone. Okay, so here is my lecture summary as customarily done. There's a signature sheet, and so please check the active learning credit list. I have updated for meeting 21, 22, and 23. And so you want to check also the slides of the topics covered. There's a lot that we have gone through, and I'm not going to go through the details because everything is listed here, except that just to run through quickly with you, as you see, motivation with the Akashi Keiko bridge, and from there we go to the 2 degree of freedom spring damper mass system, and go through dynamics, standard eigenvalue problems, generalized eigenvalue problems. So please, there's long list, so I'm not going to spell out everything. And this is week 7, that's last week. Sorry, this week, the current week. And what we have done is to recombine. Let me escape here. This is the last time we did, was to recombine the model displacement into the final displacement, right? The desired displacement in the original coordinates. Okay. That's what we did, and I don't want to get back to that. Just to want to mention to you one thing for as a way to review. Remember, this is not the first review. I have reviewed throughout the lectures, okay, throughout the semesters. So do not expect that this is going from the beginning of the semester back again. No? If you followed, come to class regularly, you have seen that I have reviewed here and there often. If this is the first time you see the material, then probably you want to look at the videos, okay, of the lectures. Here I just want to mention one thing that no one asked as a way to initiate a critical thinking question. Critical thinking question is very important because that avoids memorization. And memorization is something that you don't want to have, because memory fades easily, but the principle that you distill and keep in mind will last longer. Okay? Because our brain is finite and we cannot stuff in too many things. But if we only keep the principle, then we can derive many other things. So the question is the following. If you see, the goal was to find the model displacement, the model initial condition, right? Y at 0, in terms of the initial displacement, which is given. Okay? And the method that we went through is use orthogonality. Okay? To, in the end, deduce y at time 0 in terms of the given displacement d at 0. Maybe let me use my notes. This is meeting 21. Then I can zoom in and out at will. Oh, this is probably after meeting 21. Maybe 22, yes. So if you use orthogonality, then you can deduce the following result, right? Y at 0 equal to phi bar transpose m times d0. And the critical thinking question is, why is there a shorter way to do? Let me go back to, let me zoom out so that you can see, you know, from here. Right, this is the original setup, and then we arrive at this result here. Is there a shorter way to arrive at this result? I mean, to get to here, we need to use orthogonality. Right? Is there a quicker way? Active learning credits, or just say anything. Anything that passes through your mind is probably the best reflection of what you, of the state of your mind, your current understanding. How do you get y0 in terms of d0 if you are given d0 equal to phi bar y0? It must be a reflex, right? Let me give you a hint. This should be and this, once I write this, everyone would say, aha, well, I knew that. How do you solve for the displacement if you have this equation? What is D in terms of the applied force F?
Transpose of K, F?
Transpose of KF? Anyone else?
Inverse of KF.
Inverse. Yes. No transpose. Someone said inverse. Can you raise your hand, Kevin? Yes, very good, excellent. So 2 Kevins. Let me get my list. So Kevin team 6 and Kevin team 7.
We're going to rule the world, just watch.
Say that again.
Nothing.
Okay. So that's the hint. How do you, Kevin team 6, how do you express y0, meaning the initial, initial modal displacement in terms of the displacement, you know, in terms of the displacement of, let me show the other, this one, yeah. How do you express y0 in terms of d0? In a quick way, invert phi bar.
Yeah.
It's the same problem, right? So you can, in principle, you can write, so if y, if d 0, meaning the initial displacement, is phi bar y at time 0, then you can also write y, or there's the under bar here, meaning that's a matrix equal to phi bar inverse, okay, not transpose, times d0. Okay, and the reason that we don't do this is because the inverse is very expensive. Remember, what you learn here can be applicable to a system that has 1,000,000 degrees of freedom. So inverting 1,000,000 by 1,000,000 matrix is very, very expensive. But transposing is very cheap. It's nothing. Okay? So that's why we want to avoid the inverse. And the clever way is as shown here. Okay, using orthogonality, you see that the end result is the transpose multiplied by the mass matrix, no inverse. Multiplication, matrix multiplication is much cheaper. And then just multiply by the matrix. Okay, so that's, no one asked that question. So I wanted to point out here. So we just took care of this critical thinking questions. Okay. Now there's this is the manual of CalFam, which is the finite element code that I use to teach finite element. And you can see the eigen is the command. Okay, I just want you to focus on this command here, and you can download the manual. And if you like the code, I'll give it to you too. This is developed by Lund University in Sweden. But I want to show you this, okay, just to motivate, okay, that what you learn here is applicable in industry, in the real world. Okay, so here is my annotated manual that you can download with my annotation. And so if you click here, it will bring you to the table of contents. And I just want to show the eigenvalue, the function that computes the generalized eigenvalue problem. Okay, so here whenever you hover your cursor, and if you see a hand like this, and by the way, I use Sumatra PDF, that means that there's a live link. Okay, so you can click at the link that goes faster. Otherwise, you can go through the pages and it's slower. I give both the page number that correspond to the section as known in this manual and the PDF page number. It's faster sometimes to use PDF page number because otherwise you have to search through the section and it's not obvious. But here I provide the link for you, so you just click at the link, you go directly to the eigen function. This is just a series of MATLAB M files, and here it is. Okay, you compute the generalized eigenvalue problem. And let me zoom in. Okay, see, so now I hope that by taking this course, you now understand what it means. Okay, what the generalized eigenvalue problem. Can someone in the class, active learning credit, interpret this equation for the class? It's no longer Greek. It has to be English now. What's the English translation of this Greek equation? Can someone just state in English? Active learning credit. Dylan.
The absolute value of the stiffness matrix minus the mass matrix multiplied by eigenvalue.
Absolute value of the stiffness matrix minus the eigenvalue times the mass matrix equal to 0. Anyone else?
That's it.
Michael. Determinant. Determinant. Okay, be careful. Determinant. Yes. So in math, sometimes people use different notation. Michael, team 1, excellent. Keep doing that, Michael. And Dylan is team 3, right? Yes. Okay, so this is not absolute value, because another way you can see is the following. What's the absolute value of a matrix? You take the absolute value of all the coefficients, and on the right-hand side, this is not a matrix. This is a scalar, 0, not a 0 matrix. So over here on the left-hand side has to be a scalar. And the only way to interpret the right-hand side, even if you did not know that this is the notation for determinant, is that's the determinant of the matrix K minus lambda n. Okay? And now you know where K minus lambda n came from. Can someone quickly remind the class where this generalized eigenvalue problem came from? Just one sentence. We have reviewed that before. Dylan, sorry.
It comes from our
the
equation of motion after we use our trial solutions.
Yeah, undamped free vibration, right? So once you have the equation of motion, you look at the undamped free vibration, and then you substitute in the trial solution. Very similar to solving homogeneous equation, that you get the generalized eigenvalue problem. The van is team 6. And here I just want to motivate you to just tell you that everything that you learn is applicable in the real world and really big system, okay? Finite element. one of the most useful tools in industry. Not just for solid mechanics, but also fluid mechanics, electromagnetics, heat prop. All right. So, and we'll come back more to that because I know everyone is anxious with the exam, so I'd like to coach you more on that issue. Okay, so now we have gone through problem 1, so I'm not going to repeat that. If you search in the daily lecture summary, you see that the first time we looked at that was meeting 9, that's January the 23rd here. And if you look at my handwritten notes for meeting 9, you see I showed the class how to solve this problem 1. You know, essentially what's the principle? The principle is to find equivalent springs, right? That's really all that is. You want to simplify the problem as much as possible. And so we went through parallel springs and then springs in series. Okay, and so I'm not going to redo all this, so please, what is the underlying principle? Let's remind the class. What is the underlying principle, you know, to obtain the equivalent spring here? You saw the picture, you saw the math, the mechanics, the math. Can you state the original principle with which we used to go through all of this? Just, I know Devang already contributed. Very good, Devang. Anyone else? Matt?
The forces are equal in both
Force
springs.
equal and opposite, okay. But before that, let me show you a picture that is very storytelling, and that would remind you immediately. This one. What are the green lines here doing? Yes, please.
Euler cut method?
Euler cut principle. So Mark is team 8, and I'll like your name.
Cool.
Wait a second, please. What team number?
T2.
Team 2, excellent. I think it's probably the first time, right? Because excellent, keep doing that. And team 2, what's her name? Colton. Second time, very good, Colton. But the first time was a while ago. Yeah, Euler cut principle. So if you keep cutting and boil down to the last basic element, okay, then you can do, you know, force displacement relation. And what is also important is to look at the equilibrium of the node. Okay, that's how you sum the forces equal to 0. And you get the equation of motion in the case of dynamic, or you get the equation of equilibrium in the case of static. Okay, so and and that is in my lecture notes. You know, go back all the way to section 53. I think I can close the count fan now. Section 53 BC. You know, so and I'm not going through that in detail because please review. There's a video of my lectures that you can look at. So here, 53B. Okay, so we go through this, and you see immediately we apply Euler cut principle, right? To get the force displacement relation, and we do that for each of the 3 elements, right? That's for each of the 3 elements, and then you need to look at the equilibrium of the mass. Okay, the equilibrium of the mass is the key, is the critical step before obtaining the equation of motion. So here is still the equilibrium of the element. With the equilibrium of the element, and bring in the force displacement relation from the spring and the damper, you get this relation here. This is called the force displacement relation. Okay, you have the spring force and you have the damper force, and that's obtained by looking at the Euler cut, or equilibrium of the element. Okay, that has the spring and the damper in parallel. But to get the equation of motion, this is the critical step. You need to look at the equilibrium of the mass, okay? Meaning that you have cut everything out and only focus on the mass and replace at the cut the internal forces. Not to forget the D'Alembert force. And don't mix, okay? How many of you took dynamics or are taking dynamics? A bunch, right? A lot, 90%. Don't confuse the method in dynamics with this method. And I want to show you that because some student did ask me about that and got confused. Actually, I did explain in my notes. If you go back, you would find it, but now because of the time, getting shorter, so I just want to do it quickly here. This is a source of confusion, okay? So don't mix this up. In dynamics, what they teach you is the following. Okay, you have F, or let me write in capital letter. F equal to MA. Okay? Let's do in 1D, so we don't need the vector quantity, but in principle, in 3D, you have vector quantity. So you imitate this equation, you put the mass here, okay, and then you have the equal sign, and you repeat the mass on the other side, and then you put the force, okay, the force, I can use this is the inertial force, okay, this is MA, and then the applied force, you put F here. Okay, and this is the pictorial representation of F equal MA. That's what they teach you in dynamics. But what I'm teaching you is the use of the D'Alembert force. First, the math. The equivalent is, and I did explain this before, so this is considered as review, okay? This is not new. You just move the inertial force to the left, and that has a minus sign, and you say the sum of forces equal to 0. Including the D'Alembert force. D'Alembert force is minus the inertial force. So the picture is as follows. You draw only one mass instead of two masses, and minus MA is now drawn like this. This is MA, okay? And the sum is equal to 0. Advantage is that you don't have to draw two masses, you only draw one. And then you apply the same principle as in statics, sum of forces equal to 0. Whether the forces is applied force or D'Alembert force. Okay? Everything sum up to 0. And that's what you want to do, and that is what we did over here. Only one mass. And we have the D'Alembert force, we have the applied force over there. Okay, and then we have the internal forces due to the element of the spring and the damper in parallel. Okay, so distinguish the two methods. All roads leads to Roma. Okay, you use either method, you must get the same result. With this method, you draw only one mass. With the dynamics method, you also get the same result, but you have to draw two masses. That's all. That's all that is. No big deal. Okay, but don't mix the two together. You either use one method or the other, but not mixing the two together. Okay. So that's the issue there, and you can search too. Let's see what time do I have. Okay, I'd like to, if there's no further questions on this issue, let me bring up the problem statement. Like I said, remember last semester the student did not have practice exam problem, and they did all this. And this is the whole exam here. This time you have the practice, exam practice problem, and I also cut in half. That means that only one of the two problems. But please be prepared for both. You know, I can tell you which problem, but then some students would not study. I'm sure. So I wouldn't tell which problem so that there's a motivation to learn both. Okay, but you see that you know, it's much shorter, and you know ahead what question ask. Okay, so if there's no further questions on problem 1, I'd like to devote the time to problem 2, because actually problem 2, as I mentioned, is really a review of differential equation. Okay, but don't underestimate that, because there's this part here which is variation of parameters, and I did indicate in my daily lecture summary which section that would be in. So please look at that section. I think it's section 7. There's a video. If you're not sure, you just copy the derivation into your formula sheet. That's essentially it. But try to understand how to deduce the second homogeneous solution. Okay, this is the case where the excitation is a polynomial, but you need to remember the method of solution. Let me zoom in here. Okay. So this is a linear second order ODE with an excitation which is a polynomial. Okay, and then you have the value of the coefficients A and B, right? So the method is to decompose the problem into a homogeneous problem and a particular problem. We have gone through that before. And so this the first part is related to the homogeneous. Okay, so the whole part here is related to the homogeneous problem. Okay, and the particular problem, the particular solution is this part. Now, for the homogeneous solution, okay, I asked you what's the trial solution. First, you need to define what's the homogeneous. You know, so here in this question here, I ask you if y sub h is the general homogeneous solution, then find the equation that y sub h should satisfy. What's the answer? Matt?
Isn't that e to the lambda t?
Okay, actually e to the lambda t is the answer to the second question, the trial solution. So the the equation that the homogeneous solution should satisfy is simply the left-hand side of the ODE, right? So if you have y double prime plus a y prime plus b y equal to excitation RT, then then you decompose y into yh plus yp, okay? Where yh is a homogeneous solution and yp is a particular solution. It's all in my notes already. This is simply a review. And the homogeneous problem, or the equation that the homogeneous solution should satisfy, is the same as the left-hand side, like I said. Maybe I should write over here, and then I move to the next page later. With the exception that now you put h here and 0. Okay. That's called the homogeneous problem, that the homogeneous solution should satisfy. Okay. Could someone remind the class what's the problem for the particular solution? For particular problem? meaning the problem that the particular solution should satisfy. Quick. Here is the hint. I put down here. Can someone complete what I'm doing? You know what's the particular problem there, right?
So something RT through GFT.
Sorry?
It's not changed RT to GFT.
RT to GFT? Well, that's just notation. No. I'm talking about the problem that the particular solution YP should satisfy. This is the particular solution here. Okay.
7 YPs.
It should satisfy here. Yeah, just add YP on. Yes. That's what you want to understand and not memorize. You know, I keep insisting on understanding rather than memorization. And why? Because when you add the two together, then you would recover the original differential equation. Okay, if you add these two together, if you add these two equations, okay, then you have YH plus YP double prime, then you get Y double prime, and YH plus YP prime, then that's Y prime up there, and YH plus YP and Y. Okay, so when you add these two, and 0 plus R gets you R. Okay, so this is called decomposition into a homogeneous problem and a particular problem. So the answer to the first question is this question, this line here. The homogeneous solution has to satisfy this problem. Okay, that's the first. And then the next one would be what Mark said, the trial solution. Now you solve the homogeneous problem, right? So the next step is to solve the homogeneous problem. By introducing the trial solution. And that trial solution is the answer to the second question. Right? That means that you say, okay, assume that YH of t is e to the lambda t, where lambda is an unknown parameter to be determined. This expression was handed down to us by Euler, but it has a meaning, okay? Because when you keep differentiating an exponential, you get just the lambda coming out. So that's the answer to the second question in the test. And like I said, the idea is really to show understanding rather than memorization, and that's really what it means. Okay, so that's question 2. Yeah, let me clean up a little so that's easy to. Yeah, so trial solution for the homogeneous solution. And what is the first homogeneous solution? So this, you need to look at the characteristic equation, right, and solve the characteristic equation. Okay, when you replace the trial solution into the homogeneous problem, then you get the characteristic equation. I think I noted marked down already. And the characteristic equation is lambda square plus a lambda. And this is not memorization, okay? I wrote it down, but I expect the class to know how to derive this. Okay, if you don't, please ask. Okay, it's coming from simply replacing, like I said, this expression, exponential of e lambda t, into the homogeneous problem. We did all this. All the details are in my lecture notes. Is reviewed before you reach the characteristic equation. And when you solve the characteristic equation, you get, in principle, 3 cases, right? You have, depending on the sign of the discriminant, you have the discriminant greater than 0. Maybe we write over here. And this I also wrote many times. Discriminant equal to 0 and discriminant less than 0, right? And so this is the case where you have double real roots. This is the case, the double real roots is when the discriminant equal to 0, this is where you have distinct real roots. Okay, and when the discriminant is negative, you have, yeah, let me note down here, 2 distinct real roots, whereas here you have only 1 double real roots, okay? 1 double real roots. And here you have 2 complex conjugate roots, all right? And now, if you have only 1 double real root, how many homogeneous solutions can you find?
1.
1, yes, very good. You have 1, yeah, that's the only thing you have. But how many homogeneous solutions do you need? How many homogeneous solutions do you need? Let's let's review this case. You know, when you have 2 distinct real roots or 2 complex conjugate roots, okay, and S here, how many homogeneous solutions do you have in these 2 cases?
2.
2. But this case, you have only 1 double real root. Sorry, no S, 1 double real root. Then you can only find 1, but you need 2. And the second one is the goal of question 3. Okay. Okay, the first one, yeah. The first one already found up here. That is just coming from the single double real root. Okay, so the second one, you need to use variation of parameters to get. Let's take an example that is related to the equation of motion that we solve, right? So if you get, for example, this is only an example, okay? If you have lambda square right, equal to, let's say 9. Anything. Sorry, not this. You need to. This is the characteristic equation. Okay, if you have this as a characteristic equation, then you have only 1 double real root. That means lambda equal to 3. With a lambda equal to 3, you have only 1 homogeneous solution. That's YH1 equal to E3T. Okay, but you need the second one. Why? Because this is a second order differential equation. You need 2 free parameters. Okay. And because you also have 2 initial conditions, so you need 2 free parameters to satisfy the 2 initial conditions. And so the answer, okay, the answer is simple, but the method to get the answer, is more sophisticated. And let me put the oops. Okay, the second one is just have t multiplied in front. Okay, now to get this result, you need to use a method called variation of parameters or reduction of order. In my section 7. if you want to look at the book, it's called reduction of order. It means the same thing. Okay, but don't look up the web and find a different method, because sometimes the terminology variation of parameter is used for a different method. So don't just blindly copy from the web, and because that would not get you to the right method and the right result. So once you have these two solutions, then the complete homogeneous solution is a combination of the two. Okay, so complete a linear combination of the above two homogeneous solutions. Okay, and that is written as follows. You simply write y h equal to C1 YH 1 T plus C2 YH 2 T. Okay. With C1 and C2 being the free parameters to be determined using the initial conditions. But that only after you found the particular solution. So don't try. It's wrong to try to find C1 and C2 immediately after you obtain the homogeneous solution. Don't try to do that, because that's not the initial conditions. Okay? Could someone explain to the class the initial conditions? Why I said don't try to find C1 and C2 by trying to satisfy the initial condition at this stage. Let me begin. Remember, the initial condition has two conditions, right? Displacement and velocity. So let's say, let me use this notation: y0, right, and y prime 0 equal to, let's say, v0, okay, velocity. Why did I say that? Very good, Mark. Don't try to satisfy these conditions to find C1 and C2, Mark.
Because you still need to figure out your final solution, which is the homogeneous solution and the particular solution. So you need to bring everything together.
Yeah, so you can, very good, Mark, you can explain like this. Because y0 is yh at 0 plus yp at 0, okay? Right? At this stage, you know YH, but you don't know YP yet. So you don't have this part yet. So don't try to solve for C1 and C2 if you don't have the particular solution. You can only solve for C1 and C2 after you obtain the particular solution. Okay? Then you have two equations and two unknowns. All right? And so the particular solution, that's the topic of the next. Okay, so you see, so actually I just explained to you this question 4 here. Okay, so derive the expression for the overall homogeneous solution. That's YH1 plus YH2. That's the sum of the two homogeneous solution. How many free parameters? 2 are there in this solution. Explain the reason for the number of the free parameters, because it's a second order differential equation and you have two initial conditions that you need to satisfy. So you need 2 free parameters. But do not try to find these parameters immediately now, because that would be wrong. And you need to do this step 5 first, meaning find the particular solution, right? Only after you found the particular solution, that you can go back, combine the particular solution with the homogeneous solution. Thank you, Casey. To find the 2 free parameters. Now, one last remark. What is the equation for the particular solution? or the expression for the particular solution. This is the last remark here. You see, if you look at the excitation, whether you call it G or R, doesn't matter. The point is that it's a polynomial, 1/2 of t squared. The trial solution for the particular solution, it's better to focus on listening. Trial solution for the particular solution, okay, is the following. So if R of t is 1/2 of t squared, then you want to use this yp of t is should contain all of the power. Okay, so you can, I want to avoid C, C we already used, so let me call D, not displacement, okay? So D0 plus D1 T plus D2 T squared. Okay, and you look at my notes, D0, D1, D2 are the parameters that you need to find. Okay, and the method is in my section 7 there. You need to replace this into the differential equation that you have 3 equations for these 3 unknowns. Okay? Once you found these 3 unknowns, you get the particular solution. Okay? Section 7, assigned a long time ago with the videos as well. Okay. I think I did even mention it somewhere up here that if you go up, you would see that I have listed right here. You see, back all the way back to meeting 20. I said useful for exam 1.1 practice problem 2. Long time. Everything is there. It's lecture summary, please.